Hello everyone, this is Edward Doolittle again with Stat 100 lecture. Today I'm going to talk about 10.1 and 10.2, and so we're doing small sample statistics in this chapter. There is an interesting story about this. So it goes back to a man named William Gossett. William Gossett was a graduate from statistics program at I believe the Cambridge University in England. And when he graduated, he went to work for Guinness Brewery in Dublin, Ireland. And after working for Guinness for a while, he grew tired of dealing with so much barley. So Guinness Brewery would have to take shipments of barley, and they would come in bushels. Gossett would have to randomly choose 30 of these bushels and then test the grain in the bushels for quality. And that was because of the large sample statistics. So Gossett grew tired of dealing with all of this barley and asked himself the question, is there a way that we can do this with a small sample instead of these large 30, n equals 30 sample size? And so Gossett went back to Cambridge to earn a master's degree in statistics to study this particular issue. And part of the deal with Guinness was that he could do this as an employee of Guinness. He could go back and get his master's degree at Cambridge, but anything that he published, he could not publish under his own name. So at the end of his year at Cambridge, Gossett did finally crack the problem of how to do statistics on a small sample, and published it. And he chose a pseudonym because he had to, because of his contract with Guinness, and the very stupid synonym he chose was student. So he develops a technique called now it's called student's t-distribution, or t-test. Student's t-test. And I think this is such a terrible acronym. I avoid using it all the time. Not acronym, but pseudonym. I avoid using it all the time. It should be called Gossett's t-distribution, but that name never stuck because he published anonymously. All right, so what is the big idea behind this discovery of Gossett's? Well, it essentially goes back to the central limit theorem, as we always seem to go. And we can't really say anything. Central limit theorem says for small samples, the sampling distribution is not approximately normal. So that seems to, it doesn't say anything about what it is, and that seems to destroy any hope that we're going to be able to do statistics with small samples. However, there is a way out. So if you go back to chapter 7 and read it very carefully, it's in there. Unless the population is normally distributed. So if the population is normally distributed, then the sampling distribution is also normal. And so that gives us a way out, a way we can apply the central limit theorem to small samples. So we need to know whether the population is normally distributed or not. And that is, again, a difficult question, because if we knew a lot about the population, we wouldn't even be bothering with statistics in the first place. So we generally don't know that the population is normally distributed, but we can make a guess that it probably is in some cases. So normally distributed, how do we know if it's normally distributed? Well, one way to know is we are told that it's normally, told that it's normally distributed. And that may be the case in some problems you see in the textbook. Another way we can know whether the population is normally distributed, often biological or other complex systems lead to normal distributed populations. And the reason for that is a little bit hard to explain, but it's sort of the central limit theorem in operation. So in order for you to be the height that you are, to have grown to a certain height, excuse me, sorry about that. In order for you to have grown to a certain height, a lot of things need to have happened. So there's genetic factors, there's nutrition factors, there's what you ate, what your mother ate, there's even things like the weather, the phase of the moon. All these things contribute in some small way to why a person grows to be the height that they are. And many of these effects can work in opposite directions. They can increase or decrease, and they're essentially random, and there's so many of them that in the end, they kind of all work out, as if the central limit theorem were applied, and we get normally distributed heights. If we measure people's heights, we find that they are normally distributed in a population. And the same is true for many things that we can measure in a biological system. So we measure weights, we measure the distance between pupils of your eyes if you're looking forward. I mean, just pick any attribute that we can measure, brain size, whatever. We'll find that those attributes are distributed normally, approximately normally anyway. And that's the same not just for humans, but across the spectrum and for biological systems. If we measure the length of fish, the weight of fish, the mass of fish, if we measure the circumference of a tree, all these things tend to be normally distributed. So if we're working with biological systems, I think it's a reasonable assumption that the population is normally distributed. And the third case here is we take a sample and we graph the sample. We say the sample graph. We know a few ways of doing this: a dot plot, a histogram, stem and leaf plot. This is why I emphasize these plots way back in chapter 1, because they're coming back now. So we take a sample and we graph it, and the graph is mound-shaped. And this is of all the methods to determine whether a population is normal, this is just fairly weak. But it turns out that our statistical methods are robust. So we don't need to be absolutely sure. I mean, it's a very strong condition that the population is absolutely normally distributed, and it's probably violated in every case, that very strong condition. But it doesn't matter as long as it's approximately true. And that's what we mean when we say a statistical test is robust, is that if the assumptions are approximately true, then the conclusions are approximately also true. Stability is another way of talking about that phenomenon, that small variations from the assumptions lead to only small variations in our conclusions. So, given the robustness, which has been demonstrated by mathematicians, we're not going to, of course, go anywhere near proving that sort of thing. You can just take my word for it. Given the robustness of these of the t-test, it doesn't matter that if we depart somewhat from normal distribution in the population. And so, graphing our sample and showing that it's mound-shaped and it's roughly normally distributed gives us kind of enough evidence to proceed with our method, with our t-test. So, but best if we have something a little stronger. So if we have some theoretical reason for believing in a normally distributed population, as if, say, it's a biological system. Right, so that is a basic assumption that we are going to make for small sample to work, is that the population is normally distributed. We have to justify that assumption somehow, more or less we have to justify it. I mean, it can't be ever perfectly justified, but approximately justified. Right, so that's going to be one of our major conditions for small sample. And the next condition is that sample is randomly obtained. And that's true in large sample statistics as well. So that's not really very onerous. It's not very difficult for us to achieve a sample as random. I mean, you have to design your experiments carefully so you don't introduce bias in your samples, but that's the same problem that you face in large samples, so it's not particularly burdensome for us. So that seems to cover everything, and it looks like the central limit theorem should apply. Unfortunately, there's a little problem that is going to throw us off. And this is worse the smaller the sample is. So when we get up to about 30 large sample, this discrepancy is going to disappear. But for smaller than 30, we're going to see a kind of a notable discrepancy. And the problem is kind of funny. You might not have predicted it before, but I have talked about it. It's that we have been approximating the standard deviation of the population using the standard deviation of the sample. We've done this all the time in Chapter 8 and Chapter 9. I do this approximation just regularly. The problem is that only applies for a large sample. That relationship breaks down for small samples. And this is the real source of our issues with small samples. So what we end up doing is we have to calculate our statistic. And it's going to look like the Z statistic, but it's not going to be distributed like a Z statistic because this is not the case. S is unknown and X is unknown, so there's more that's unknown about this situation than there was in the large sample case, where the large sample case, S was approximation for sigma. So, that was not sort of unknown or random. I mean, I guess should say random here. Random. So there's more randomness in this expression for small samples than there is for large samples. There's more variability in both S and X than there would be for a large sample. For a large sample, S is kind of anchored by sigma because of this relationship for large samples. In the small sample case, this S can drift considerably and unpredictably away from sigma. So that means that there's some more randomness here, and you have to very carefully sort it all out, and that's exactly what William Gossett did. And what he found is that there is another distribution that we're going to. This is the t distribution, or the student's t distribution, which I would wish was called Gossett's distribution. It looks very much like a normal distribution. It isn't the same though. Here's a normal distribution. Oops. Let's ignore that. A normal distribution kind of has a higher peak and narrower tails. T distribution has a lower peak and fat tails. And one other issue with the t distribution is that the mathematics of the t distribution depends on the sample size. So for the z distribution, it was always the same shape, no matter what the sample size. If it's 30, if it's 100, if it's 300, the sample distribution, the sampling distribution for z is always the normal distribution. It's always the same shape. The shape of the t distribution changes as n changes, so that causes a complication. We would have to have, about 30 t tables to do this the same way as we do the z table. For each value of n, so that's like, I don't know, we could probably cut that down not from 30 but to 29, 28 tables. Anyway, that's still a lot of tables. You don't want to have to print out 28 tables to come into the final exam, to write the final exam at home, as we're going to do in this coronavirus edition of the course. But anyway, 30 tables is too much. We can't have an appendix with 30 tables in it. It would take up too much space, drive up the price of your textbook. We'd kill a forest of trees every time we printed stuff out for final exams. So we don't use all 30 of these T tables. If you're using a computer, there's less of a problem. A computer can easily store 30 different tables in its memory. So computers can deal with this just fine. Unfortunately, we are not using computers in this course. We're using paper tables, so you have to be able to cope with. We have to figure out a way to cope with this. We don't want to print out 30 tables. So what we do instead is, for T tables, we only print out the critical values. So the T tables look very much like you remember this Z table. We had alpha is, 10%, 5%, 2%, 1%. We had Z sub alpha. We had alpha over 2 and Z sub alpha over 2. I'm not going to write out this full table, but you remember this. We've used it many times. If you've been doing your homework, you've referred to this table many times. So these give critical values of Z. For specific chosen alphas. The popular ones are 10, 5, 2, and 1. Our T tables are going to look the same. they're going to look very similar, except we're going to write them this way. We're going to write alpha across the top. We're going to have and down the side of the table, we're going to have degree of freedom. Oops, degree of freedom. So I said that the tables depend on n, but we don't actually, for kind of theoretical reasons, we don't use n in our table. We use some concept called degree of freedom, but there's a very close relationship between n and degree of freedom. Degree of freedom is just n minus 1 for this case. Degree of freedom is a theoretical concept, and I don't want to go into all the details explaining it. We're going to counter it a little one more time in this course, but maybe twice more in this course. But in this case, all you need to know is that there is this relationship between n and degree of freedom. And so our table gives df is, can't remember if it starts at 1 or 2. Well, let's just say 1, 2, df is 3, df is 4. Right, and so that corresponds to n is 5, n is 4, n is 2. Okay, so for technical reasons, theoretical reasons, our tables are written in terms of df's instead of n's, but there's this relationship. Okay, and so alpha, and we also have to have a distinction between one-tailed and two-tailed. And so there's going to be alpha. We have to be careful of whether we're dealing with alpha or alpha over 2. And different tables write this in different ways. So I have published tables on the website, which I think I would prefer that you use. I think they're easier to use. There's also a table in the back of the textbook, and it doesn't have the alpha over 2's in it. So I think it's more confusing than the table that I have put in the website. So I urge you to take a look at the tables from the website. You can also find the T-tables in Appendix 1, Table 4 of the textbook. So I'm just leafing through them right now just to see how they're written. Yes, and these tables, Table 4, Appendix 1, looks exactly like the table on the back cover of the textbook. So in a pinch you can use it, but it's a little bit harder to use than the table I put in the Your Courses site, because the table I put in the Your Courses site helps guide you through one-tailed versus two-tailed. The tables in the back of the textbook and in Appendix 4 really just have the one-tailed version, and you kind of have to think a bit harder about how to do this for two-tailed. Okay, so that is the overview of the T distribution. Now let's just walk through one example of this. So we're going to take a look at problem example 10.1 in the textbook. So the question is, for a T distribution with 5 degrees of freedom, the value of T that has area 0.05 to its right, that's what we want to find. So we want to learn how to use the textbook to find, wow, that was the straightest line I ever draw. It was my iPad helping me here. Okay, so here is our t distribution. And it's supposed to be symmetrical. It has that symmetrical property, just like the z. Whenever I draw it, it comes out looking suspiciously like a z. It is similar to the z. It's not exactly the same, but I don't care for photorealism when you're drawing these sketches. All that matters is kind of general impression. Okay, so what are we looking for? We want to find the value of t that has area 0.05 to its right. So we're going to graph that. This is very similar to the questions that we might come up with in Chapter 9 for hypothesis testing, one-tailed hypothesis testing. But this is a t distribution. And we have degree of freedom is 5 degrees of freedom. And that, of course, means that n is 6. Okay, so we have this, this situation. Now we want to use the t-table, either in the textbook or better from the website, to find that number. So what we're going to do is look up the alpha is 0.050. And that's this here, column. And then the degree of freedom equals 5 row in the table. And when you do that, you should find that the magic number is 2.015. All right, so that's one way to use the t-table. So in a degree 5 situation, n equals 6 small sample, we are going to find that a randomly chosen sample will be distributed so that only 5% of the time the t statistic will exceed our critical value of 2.015. So that is how we employ the t distribution. We need to use this whenever we are dealing with a small sample. So for n less than 30 is a small sample for us. Notice that the values are different. So the 5% line, what was this for the z distribution? I will ask you that question. You should be able to look that up in your table or just know it offhand. For z, what was the critical value at 5%? And see that it's different from the t-value. So we really do have to use the t-distribution for small samples because we're going to get different critical values. All right. We can also do the same thing on the left. So the textbook does that on the left, and we can also do the same thing for two-tailed distributions, but we will talk about that in the next section, 10.3. So I would encourage you to now study 10.2 very carefully. We have a sample size of n is 10. And so that means the degrees of freedom, the number that we use is 9 for this. We have 1% of the values, so we are interested in cutting off. Okay, that doesn't look at all right. I think that's so bad I'm going to have to delete it. Okay, there we go. Let's try that again. Oh, no. Oh my gosh. That is awful. Okay, one more time. I am no artist. Okay, good enough, kind of lumpy, but all right, whatever. I'm going to stop while I'm ahead. Okay, so I want, in this case, 1% to the left. Oops. T is 0, where's this symmetry point here? Our table gives me at 1% 2.821. So df is 9. I'm looking for t at 1%. Table says that is equal to 2.821. And remember, on the left, numbers are negative. Okay, so that is the answer to example 10.2. This is 1%, and at 9 degrees of freedom, the critical value is negative 2.821. One interesting thing about this is that as degrees of freedom approaches 30, the t critical values tend to stabilize near the z critical values. That is where the magic number 30 comes from. So in reality, we should always use the t distribution. We would not be wrong if we always use the t distribution. But we find that there's little practical difference between t and z when around 30 degrees of freedom. So that's kind of gives us license to use the simpler z distribution when we have a large sample. Okay. That is pretty much it. That is the big picture for the t distribution. We haven't covered two-tail just yet, but that is coming. And otherwise, we've talked about all the introductory material. So I'm going to end this now, and I'm going to come back and we're going to talk about 10.3, and then we will be done with chapter 10. 10.3 is the end of chapter 10 for us. There's much more to chapter 10, but we are not covering it in this course. It's not part of the course. So we're just doing the very simplest applications of the t distribution. Okay, so that's all. I will see you again soon. Bye.